Hello everyone, I'm Indrajit Bhattacharya from TCS Research India, and I'll be presenting our paper titled Discovering Knowledge Graph Schema from Short Natural Language Text via Dialog. This is joint work with my colleagues Subhasis, Ghosh, Arpita, Kundu, and Aniket. Pramanick. Knowledge graphs are becoming more and more common in AI applications. We focus on knowledge graphs with a schema. This means that the entities and relationships are both associated with types. For example, Tom Mitchell is an entity of type researcher, and the researcher type is connected to the paper type through the publisher's relationship. Now, the benefit of having a schema is that it enables semantic interpretation and reasoning. On the other hand, creating or expanding schemas is difficult for human experts. We propose having a dialogue with a human expert for schema enhancement. Now, asking a human expert for a schema or a schema expansion directly is difficult. Instead, we take short natural language statements, such as Tom Mitchell works on never-ending learning, and then we ask the expert for schema paths or annotations of such statements. For example, researcher Tom Mitchell leads project exploring topic never-ending learning. And then the overall schema is obtained by aggregating the schema paths of such individual statements. Now, asking the expert for schema paths of natural language statements is similar to active learning for structured prediction. However, in the active learning setting, the expert is asked for the schema annotation or structured annotation of a natural language statement in one shot. However, real experts do not like answering questions. In fact, when asked a question with a significant number of options, the expert is likely not to respond at all. This is what we call response uncertainty on the part of the expert. In such scenarios with response uncertainty, active learning, unfortunately, does not make much progress. In addition, active learning frameworks cannot work with expansion of the structured space, for example, with new entities and relationships, as in our setting. So this is a one-slide summary of our main ideas. In order to make progress with response uncertainty, we decompose a query into a mini dialogue having a sequence of mini queries of different types. We model response probability of the expert for mini queries using the complexity of the mini queries. And the parameters of this response probability model are estimated from the dialogue as the dialogue progresses. We propose a dialogue strategy that maximizes expected utility of a mini query, considering all possible responses to the mini query, including no response. And finally, we allow the candidate paths to include new types of relations. This enables the expansion of the schema. Okay. In this slide, we see an example mini dialogue on a natural language statement that consists of a series of 8 mini queries, and they together obtain the path for the statement in pieces. Here, the agent is already aware of the researcher entity type, and in the first query, it asks the expert whether Tom Mitchell is of the researcher entity type. In the second query, it focuses on Nell and asks whether this is of type paper or topic. In the third and fourth queries, it asks the expert whether the path between researcher and topic goes through a new entity type that is not currently in the schema. And in the next query, it asks the expert for the name of this new entity type. And this dialogue continues in this fashion until the entire path has been confirmed by the expert. Okay, so what are the different types of mini queries? The first type is called which of. Now consider the entire set of candidate paths with their probabilities. The which of query takes the entire candidate set and asks the expert which one of these is the right path. there are 2 points to note here. This is the only query type in active learning. Secondly, this works well when the set of candidates is small, but is unlikely to make progress for a large set of candidates. So what do you do with a large candidate set? If you cannot reduce this, the set of candidates to a single one in one shot, as with a which of query, then you try to reduce the uncertainty to the extent possible. And this is done using an any of query. This picks a subset of the candidate set and then asks the expert if any of the candidates in this subset is the right one. Now, this can either be done by enumerating the subset, as in this example, or it can be done by picking a discriminating feature of the subset with respect to the complement. For example, instead of enumerating the paths, the query could ask whether the statement is about the project entity type. Now, this can be significantly helpful if such a query exists, because it is much simpler and therefore more likely to get a response from the expert. Finally, we have to have a query that asks for the names of the new entities and relationships that are found during the dialogue. And this is done using a name query, as in this example, which asks for the name of the new entity connecting researcher and topic. So the overall mini dialogue format consists of a sequence of any of and which of mini queries. And we call this the mixed any which mini dialogue format. As we can see, this is strictly more powerful than the active learning dialogue format, which reduces to the active learning format when the entire mini dialogue consists of a single which of query. All right, so how likely is the expert to respond to a particular mini query? So we say that this is a function of the complexity of the mini query, and we model the complexity as the sum of the path lengths in the mini query. As the complexity increases, the no response probability also increases. And we model this with the generalized logistic function, as you can see here, with parameters W and T. And the agent estimates these two parameters as the dialogue progresses based on the actual responses and no responses obtained from the expert for different mini queries. All right, so now we come to the overall dialogue strategy. So given the current set of candidate paths, the dialogue strategy considers all the possible mini queries of the two types that can be posed for the current candidate set and decides which one is the one to ask next. This is done using the notion of expected utility or reduction of the entropy over possible answers to the mini query. And this considers no response as one possible answer. Now, the other thing that the dialogue strategy needs to do is pick the next statement for performing a mini dialogue. And this is again done using the notion of expected utility of the best mini query for that statement. We call this the expected utility based dialogue strategy, or EU dialogue strategy in short. Again, we can see that this is strictly more powerful than the entropy based active learning dialogue strategy, or EAL. In fact, the EAL strategy falls out as a special case of the EU dialogue strategy when the expert is certain to answer and the agent is aware of this. And finally, how do we get the candidate paths and their responses to begin with? This is done. Remember that the candidate paths need to include the new types, relationships, and edges. So we extend the path ranking algorithm of Lau et al. From EMNLP 2011 to account for new vertices and edges in the random walk. Here is a quick snapshot of experiments in the interest of time. We experiment with statements from the tcs.com website, and we compare against a bunch of baselines including the active learning, entropy-based active learning baselines, and an ablation of our strategy EU that does not estimate the no response parameters. Recall that the active learning based baselines assume certain response from the expert. In our first experiment, we look at the detection task, where the agent only needs to detect known entity types and relations in the schema paths. This is the only experiment where the active learning based baselines apply. And as we can see that the EUL strategy with learning in red clearly outperforms the other strategies in terms of the learning curve. I'll point out that the active learning based strategies do not make much progress at all, by mainly because of the incorrect certain response assumption. In the second experiment, we look at discovery, where the agent actually needs to discover new entities and relation types in the test set. And here we say that the discovery agent, EUL, slowly catches up with the detection agent, which is the skyline. Again, recall that the active learning based baselines are unable to address this task. So I'll summarize by saying that our proposed expected utility based dialogue strategy with learning that accounts for response uncertainty from the expert clearly outperforms existing strategies in terms of discovering the schema from natural language statements. So thank you for listening to me, and we'll be happy to hear from you.